In this screencast, I want to talk about the binomial theorem, and to get there we need to look at some examples and to set some terminology. So here, for instance, is the expression x plus y raised to the first power, and as of course is obvious, that's just the same as x plus y. Here we've got x plus y raised to the second power, and as you remember from high school, that turns out to be x squared plus 2xy plus y squared. So what does this have to, why do we use the word binomial? We use the word binomial when we're talking about these things because there's two variables that are being summed together and raised to a power. And they don't have to be variables, but two terms that we're adding together and then raising to a power. So let's think about the third power, x plus y cubed. Now, I want you to think about this in a way that you probably may or may not have thought about in high school. But let's just let's write it out, what raising it to the third power means. That's x plus y times x plus y times x plus y. And now let's think about where each term comes from. If you remember, and you've probably seen this before, the resulting expression is x cubed plus 3x squared y plus 3xy squared plus y cubed. So where do the coefficients here come from? Well, there's a coefficient of 1 on the x cubed. Where does x cubed come from? It comes from choosing an x from here, choosing an x from here, and choosing an x from here. So from every term, we get x cubed by choosing x from every term. The next one, we have to get an x from two of the terms, say these first two, and a y from the other term. Or we could get the y from the middle term and the two x's from the outside terms. Well, it turns out there's three different ways to choose two of these terms. So what we get is we have 3 times x squared times y. And then what about the x y squared term? That comes from choosing one of these terms for x and the remaining terms for y. And how many ways can you do that? Well, this could be the x term, so that would be 1. This could be the x term, that could be the other one. Or this could be the x term. So there's 3 different ways for that. And then for y cubed, we don't want any of these terms to pick out x. So there's exactly one way to do that, and that's y cubed. So pause the video and try to write out the expansion of x plus y to the fourth. Well, after giving that a try, hopefully you came up with something that looks pretty much like the following. Again, let me walk through where this comes from again. We've got 4 terms up here. Think of these as labeled, so you can think of them as being in a set and with 4 different elements. Call this x plus y a, this plus x plus y sub b, x plus y sub c, and x sub y sub d, but 4 different terms. And to get x to the fourth, we have to take the x from each one of the 4. And there's only one way to do that. That's x to the fourth. Then to get x cubed y, we have to take an x from 3 of the terms and a y from 1 of the terms. Well, how many ways can you choose 3 things from 4 things? Well, that's c, 4, 3. And that turns out to be equal to 4 if you multiply it out. Same thing here. We want x squared y squared, which means we have to pick out 2 of the terms for x, 2 for y. So we could do that way, or we could do it this way. Take the 2 middle terms for x and the 2 outside terms for y. At any rate, there are 6 different ways to do that, so that gives us 6x squared y squared, etc. So this idea can be generalized, and you get the following formula. If you want to compute x plus y to the n, that's just the sum from k equals 0. Okay, so that would be picking out nothing out of the set of n elements, and up through n. Right? So our set here are the n different factors over here. And when we do that, we pick out k elements, and those correspond to x to the k, and then the remaining n minus k factors correspond to y to the n minus k. Now, you'll notice, of course, that I've switched the notation here on you. This is the traditional notation that's used in the binomial theorem. We say this expression here, the binomial coefficient nk, and it's equal to the combinations of n things taking k at a time. So this is something you already know. It's just c and k for combinations, and we just write it differently because of the tradition that's associated with the binomial theorem. So at this point, you should practice. Write out the binomial expansion of x plus y to the fifth using the same kind of argument that we used before, where you're going to get, in any given time, you're going to get the combinations of 5 things and then k, right? And k is going to be the exponent of x in that term. As you've seen, the binomial coefficients are the same as the number of subsets of size k from a set n. And again, just want to emphasize this because that's really the whole point of this screencast, is that each subset can be thought as a subset of the n factors of x plus y to the n. And these are exactly the factors that contribute x to a term in the expansion. So here's a real simple application of this. Remember that the power set of A, the cardinality of that, is equal to 2 to the cardinality of A. So if we have 5 element set, then if A is 5 elements, then the power set contains 2 to the fifth, or 32 subsets. So notice that in writing, if we write out the binomial expansion using the binomial theorem, if we write that out, we're going to have a sum from k equals 0 to n of c and k times, we've got terms x raised to a power, y raised to a power. And I think we can prove, you should be able to prove this theorem here, that in fact the number of subsets of size k, if you add up all the different sizes, that's going to be equal to 2 to the n. I mean, certainly if you add up all the different sizes, that's going to be how many subsets are in the power set. So we now have another way to show this other than sort of reasoning about it like I just did. Because we've got the binomial theorem like this, can you find values for x and y that'll give this identity? Okay, so what should x be, what should y be, so that on one side you're going to get 2 to the n, and on the other side you're going to get the sum from k equals 0 to n of the binomial coefficients. Give that some thought before you go on to the next slide. So the key here is this first bullet here is just a recap of the last slide. The key is to just let x equals 1 and y equal 1. Then you're going to have 1 plus 1, okay, that's 2, raised to the n. I'll give you that side. And on this other side, you're going to get this summation and x to the k. Well, x is just 1, so that's just equal to 1. And y to the n minus k. Well, y is just 1, so that's just 1. So we're going to get the summation from k equals 0 to n of binomial coefficient nk is equal to 2 to the nth power. So now, try and see what happens if you let x equal 1 and y equals minus 1. And do it for, say, n equals 4 and n equals 5. So do it for some particular examples. So hopefully this has helped you understand the relationship between the binomial theorem and subsets, and we're going to take this a step farther in the next screencast.